Okay, are you ready? We're going to look at the phase portrait for our last example of this damped harmonic oscillator. And what we're going to do is we're going to use a new website. The old website works. We can plot direction fields using the old website, but I have a new website specifically for phase portraits, and it is pretty neat. The link can be found in Canvas. So if we go over here and, oops, that's the old one. Again, it can also plot direction fields. If we go over here and type in what we have the second derivative, right? If we'll have to type this in as system. Remember, writing it as a system of equations is going to help for qualitative analysis. That's what we're going to do for a phase portrait, is write it as a system. We have an autonomous differential equation, which is really nice. And well, wait, how do we write this as a system? Right? Well, let's think about it. Right? What we have, if we have this in a system, is how do I want to write this down? Right? Let me just copy down what we had before. Hopefully you know how to turn this into a system, because it's the same every time. Any second order differential equation we transform into a system the same way. All right, we're just going to say, all right, the derivative of the first with respect to time is some new variable. You call this whatever you want. And the second derivative of y with respect to time, well, you just solve for this. So we're going to subtract 3 times that. This is just what we called v. And we're going to subtract over the 2 times y as well. And hey, we got a system. Wonderful. All right, so let's plot that using this new plotter. And again, have to go over here. We're going to have, this is just v, which in this case is y. And we're going to have a change of variables to make things match with this plotter. And the other one is going to be -3 times y minus 2 times x. Again, slightly different variables. And we're going to look from -2 to 2. We can change t. We can change a lot of things. Let's just hit graph phase plane. And when we graph the phase plane, we are reminded of this. Multiplication must be written explicitly. So we go and do that. We follow directions. And now we graph the phase plane and we get something quite interesting. Notice this is not a direction field. Notice this is a vector field. And that's one of the nice things about this plotter is you can actually choose whether you want a direction field, which has the same length arrows, or a vector field. You can see both. And you can see, again, different information from both. The direction field, which all has the same length, is a lot of times cleaner. But the vector field can really show you a little bit more information about time. How are things happening? At what speeds are things happening? And so you can see that things are progressing much more rapidly. Things are changing much more rapidly for high values of position. Remember, position is our horizontal axis and velocity is our vertical axis, right? So the velocity is changing very fast when we are at this initial condition. Velocity being the vertical component here. And then just like before, we can click on different solutions for initial conditions, or we can type them in down here, I believe. Yes. So anyhow, we were looking at initial conditions of the initial position is 1 and the initial velocity is -1. So initial position is 1, initial velocity is -1. What happens? We start here at this dot and we go towards equilibrium, right? The things are, again, we don't really have an idea of how time works, but again, that's kind of a cool thing about this plotter is you can kind of see time progressing as a color. So this purple length is the same amount of time as this dark blue length, which is the same amount of time as this light blue length. Kind of hard to see here. We had another initial condition that also had another interesting thing happening here. Again, if we started at 1, -2, a position of 1 and a velocity of -2, we saw also that there was no oscillation at all, right? We saw down here that we just approached like so. There's no oscillation. We just approached equilibrium. And again, you can see the time component using the color feature of this website. But I told you, right, that there are more interesting solutions as well. There is oscillation, right? This is a damped harmonic oscillator. These are kind of weird special solutions for specific initial conditions. But let's say we started somewhere else. What if we started over here? Specifically, what if we started with a negative initial position, so the spring is really compressed, and no initial velocity? Well, we think if we start with a compressed spring and no initial velocity, when we release it, the spring will shoot out, and then it will compress back, and then it will oscillate a little bit before going back to equilibrium. And we can see that this is what we get. All right. So again, this really depends on the spring constants and a lot of other things. But again, you can actually see here that we also have very little oscillation here. Right? Position is decreasing, position is decreasing, velocity is also decreasing. Velocity increases for a while, velocity being the y component here. Things decrease. Again, we can find other solutions as well. And you can actually see that for this system, for this spring, we actually don't have any oscillation. Or no, I think we do have, yeah, we do have some oscillation, right? If you look at this initial condition, we start with a negative position. We cross equilibrium, which is x equals 0. And then we come back. So there is some oscillation, but it really depends on the spring constant, the mass, and such like this. And actually we have something, and I really should have planned this ahead of time. We have something in Canvas as well for you to look at if you wanted to see how this might look. And if we do that, this is sort of what we get. I'm on the wrong window now. Right. So this tool is over here that can kind of see it. We can model it. So again, if you start fully compressed, you can see short oscillations, and then it's going to get that equilibrium. And again, that's going to depend on the mass. It's going to depend on the spring constant, which we can adjust over here. It's going to depend on a lot of things. You can see, you can play with this. We'll get into more of it later as well, but some sort of visualization for what we have with spring constants. Okay, so those are kind of the main things. Remember how that connects to these solutions right here. Some initial conditions, initial velocity and initial position. Some initial conditions really will have a little oscillation, but these are special ones. These are very special ones. They have no sine or cosine component here at all. We'll talk about where these special ones come from in chapter 3. But we're gonna end this section really right now. We're gonna end with a couple of questions that I want you to be thinking about. Specifically, why are these some special solutions? How would we find the solutions that oscillate a little bit? What initial value problems can we even solve this way? Hint. We're going to be solving a lot of linear equations, linear systems. Constant coefficients are always good. And specifically, you might also ask yourself, when we were solving this quadratic equation, we had 2 real roots. That's real nice. What happens if we have complex roots? How does that affect our phase portrait? Well, we'll also talk about that in chapter 3. And then that's pretty much it. We're going to be looking, chapter 3 really does talk a lot more about damped harmonic oscillators. So in the linear systems that we're looking at, we really will come back to this example over and over and over again. This really is kind of an introduction section to, what are damped harmonic oscillators? What do their differential equations look like? We can write it as an equation or as a system. How do we interpret those phase portraits? Again, we got that new website, which is really nice. This one over here. A different way of seeing phase portraits. And again, you can see vector fields, direction fields. It does kind of incorporate time with this plotter by color coding things, which is pretty nice. But yeah, that's pretty much it for this section. Hope you enjoyed it. Hope you got to see some cool stuff. And that's it until next time.